Our understanding of the universe has already been overturned several times. Let us recall in passing of the astronomical worldview which our ancestors possessed, where Earth embodied the center of the cosmos, circled by all remaining objects. In the meantime, however, we know that our blue home planet is no more than a tiny piece of the mosaic in an overwhelming construct that we still haven't deciphered. It is thanks to experts like Edwin Hubble that we understand our galactic home more precisely than ever before. The American achieved several milestones in the course of his life. He classified the spiral galaxies, researched the expansion of the cosmos, and last but not least, came across the Hubble constant. But why is this fundamental parameter of cosmology so important? What answers can this parameter give us? And finally, why do the latest observations of the Hubble Space Telescope suggest that something is wrong with our understanding of the universe? Together with you, we would like to take a closer look at this exciting topic today. Excited about the groundbreaking discoveries and unique spectacles in the universe? Then remember to subscribe to Simply Space and click the bell for regular updates on these exciting topics. By giving us a thumbs up, you're motivating us and showing that we can keep you excited with the content of our posts. The discovery of the cosmos. On January 1st, 2022, the universe celebrated its 97th birthday. Well, this is true at least for us humans, because actually, in 1925, US astronomer Edwin Hubble succeeded in proving that the Andromeda Nebula is outside of our native Milky Way. Hubble's scientific work was to lead to a revolution in the general understanding of the cosmos. With his discovery, the expert paved the way for the knowledge of an expanding universe, which researchers would eventually trace back to the Big Bang. In addition, Hubble encountered an unexpected pattern while observing other galaxies. He recognized that the spectra of different galaxies are by no means equally shifted into the red and blue, but that significantly more red-shifted spectra exist. Interpreted as Doppler effect, this means almost all observable galaxies are moving away from us. But that's not all. Hubble also recognized that this pattern is directly related to the spatial distance. The farther away a galaxy is from us, the faster it drifts away from us. Meanwhile, the Hubble constant is one of the fundamental quantities of cosmology. But what does this fundamental parameter actually indicate? In simple terms, the Hubble constant establishes a direct relationship between the recession velocity of a galaxy and our spatial distance from it. By means of this value, we can thus calculate how fast the steady expansion of the universe is taking place. Strictly speaking, however, this is not a constant. Since the corresponding value changes in the course of time, we often speak of the Hubble parameter. Furthermore, this quantity allows us not only to detect present developments, but also to look into the past, respectively, into the future. From the Big Bang to the end of the universe, the Hubble constant gives us a detailed insight into the fate of the cosmos. Well, at least in theory, because in fact, it's anything but easy to quantify this parameter. The Hubble constant. To decipher the Hubble constant, we need different basic quantities: the recession velocity of a galaxy and its distance from us. The rate at which a galaxy recedes from us as a result of the expansion of the universe can be measured by observing the wavelength shift. The so-called positional change of spectral lines in the emission and absorption spectra is called redshift. However, the determination of the second parameter, which we need to decipher the Hubble constant, turns out to be comparatively problematic. One approach to this problem is to study Cepheids. These are a special group of stars whose brightness fluctuations are strictly periodic. By comparing the apparent brightness and the luminosity, it's possible to determine distances, which is why the Cepheids have had a special status in the world of astrophysics for quite some time. Edwin Hubble also used this cosmic standard to calculate distances in space. However, the distance measurement by Cepheids is limited. This is due to the so-called blending effect. In essence, this means the superposition of several stars due to the limited resolving power. Or in other words, The measured light of a Cepheid is in reality often the sum of the light of several stars. Because of this, the apparent location of the Cepheid appears brighter than the star is in reality. So it happens that the distances to Cepheids, which are outside our home galaxy, must be corrected by empirical formulas. Therefore, it can be stated, the farther one of these standard candles is from us, the greater the potential for error. This is also shown to us by Edwin Hubble's original work. The astrophysicist examined the distances and recession velocities of 46 galaxies. Based on this, he determined a value for the Hubble constant, which he put at 310 miles per second per megaparsec. A small classification, a megaparsec corresponds to approximately 3.26 million light-years, and a light-year again is 5.88 trillion miles. A comparison with modern data shows, however, that the Hubble constant is nowadays put at a value between 42 and 46 miles per second per megaparsec. This is not least due to the fact that modern researchers have access to far more precise instruments than Edwin Hubble was able to use in his lifetime. Explosive helpers. Where the study of Cepheids reaches its spatial limits, Type 1a supernovae come into play. Remember, a supernova is the explosive death of a star. In the course of this process, the dying celestial body briefly reaches millions or even billions of times its original luminosity and shines as brightly as a full-grown galaxy. A Type 1a supernova can be identified by measuring some spectroscopic criteria. These include the typical absence of helium and hydrogen, as well as the detection of strong silicon lines. And indeed, the study of such events in the recent research past should help to determine distances and further constrain the frame values of the Hubble constant. Unfortunately, however, it's not enough to merely bolster this parameter with recent data. To ensure as far as possible that the Hubble constant is correct, theoretical values from the past must also be taken into account. In order to achieve this, the experts turn their attention to the birth of the universe and repeatedly encounter insurmountable complications there. Inexplicable deviations. If we succeeded in determining the expansion rate of the universe shortly after the Big Bang, we could use this value to apply it to the Hubble constant of the current scenario. As we now know, enormous amounts of energy were released in the course of the Big Bang. Thus, as the cosmos continued to expand, the radiation also became steadily more redshifted. To understand how this redshift took place in detail, it's worth taking a look at an exciting remnant of the galactic birth, the cosmic microwave background radiation. This nearly isotropic radiation arose immediately after the formation of the universe and is considered outstanding evidence for the Big Bang theory. Based on the current nature of the background radiation, the experts can draw important conclusions about the evolution of our galactic home. The researchers combine these physical principles with estimates of the original mass and energy quantities. As a result, it's thus possible to create models that allow us to trace the expansion of the cosmos back to its initial state. However, this endeavor has also led to one of the greatest crises in modern cosmology. The theoretical values simply do not agree with the actual observation data. Thus, the mathematical predictions say that the universe should actually expand much slower than the information collected by the Hubble Space Telescope indicates. To get to the bottom of this puzzling discrepancy, the SHOES team put an ambitious undertaking into action. Using the data collected by Hubble, the experts examined 42 supernovae, the equivalent of a nearly complete analysis of all the stellar deaths identified by the complex instrument. Eventually, the scientists calculated that the Hubble constant settled on a value of 45 miles per second per megaparsec. While this is still slightly higher than the theoretical models say, given the lush sample size, the probability of a misestimation was put at 1 in a million. Although the background for the still present discrepancy remains uncertain, the new results should provide an important cornerstone as cosmological research moves forward. In fact, experts are already looking for new alternatives to the standard candles used so far. While Type 1a supernovae have long been considered the most accurate standard candles for determining cosmological distances, this assumption is being challenged by recent findings. Currently, neutron star mergers and red giants are considered promising candidates when it comes to questions about future determiners. As in so many other subfields of current research, experts' hopes lie in the planned use of the James Webb Space Telescope. According to the report, Webb is up to 100 times more sensitive to electromagnetic waves than the Hubble telescope. As the most powerful space telescope of all time, James Webb is to present the universe to us in unprecedented detail. In doing so, the complex instrument works from the red part of visible light to the mid-infrared spectrum. As mentioned earlier, distant and thus early regions of the cosmos are shifted into just that range of cosmological redshift. Therefore, experts hope to gain important insights into the first luminous objects and galaxies that formed shortly after the Big Bang. Provided everything goes according to plan, Webb will begin its scientific service in a few weeks. The universe fascinates us above all with its exuberant diversity. When thousands and thousands of objects sparkle in the sky on starry nights, we realize time and again how small we actually are. Apart from these countless breathtaking celestial bodies, however, there are also regions in the cosmos that are characterized by an oppressive emptiness and an impenetrable darkness. But what are these areas? Which riddles are still to be solved in this respect? And what influence do these gaping voids have on the surrounding structures? Together with you, we are looking for answers today. Gigantic void. As we all know, our Earth revolves around the Sun during its galactic journey. Our mighty host star does not embody a rigid structure either. It races around the center of the Milky Way at a speed of 137 miles per second. But even here, the cosmic merry-go-round is far from coming to a standstill. Together with the mighty Andromeda galaxy and about 70 dwarf galaxies, our Milky Way is part of the so-called local group. This cosmic collection comprises objects within a radius of 5 to 8 million light-years. Researchers assume that the individual components of the local group are gravitationally bound to each other. With a share of 95%, we find the largest part of their visible mass in our Milky Way and the Andromeda galaxy. In detail, however, the individual group members are not evenly distributed, but form individual subgroups depending on their gravitational binding. Computer-aided simulations came to the result that the local group might host up to 500 dwarf galaxies. However, only about 70 are known to us. In this regard, some scientists believe that those galaxies we have not yet been able to detect are largely composed of dark matter. This overwhelming galaxy collection is directly bordered by a bizarre area called the local void in the ranks of astronomers. As this term immediately suggests, this gigantic area is characterized by its unexpectedly sparse stellar population. The exact size of this empty space region has not yet been determined. According to current estimates, the gaping void has an expanse of 150 and 230 million light-years. Thus, the local void trumps the local group in terms of size many times over. The corresponding area can be divided into 3 separate sectors. The individual regions are separated from each other by so-called filaments. These are filamentary connections composed of visible and dark matter that lie between large galaxy clusters and superclusters. On the largest known scales, the cosmos appears as a kind of galactic web formed by these same filaments. The areas enclosed by this honeycomb structure are in turn called voids. Compared to their volume, however, voids contain very few galaxies. Position and influence. Gravity causes a striking distribution pattern in the universe. It causes matter to clump together, in colloquial terms. As a result of mass attraction, galaxies thus come together in the form of clusters and chains. Between these cosmic accumulations exist areas in which we find only very few or no galaxies at all. Before experts became aware of the gigantic void that surrounds us, they found out that the Milky Way is part of a large, flat galaxy cluster. This so-called local sheet also embodies the boundary region to the ominous local void. The current conjecture is that our blue home planet is located about 23 megaparsecs from the center of the local void. 1 megaparsec equals about 3.26 million light-years. To determine the approximate size of the empty area, the researchers turned their attention to an isolated dwarf galaxy. As a general rule, the larger and emptier a galactic void is, the weaker its gravitational pull. As a result of this principle, the faster the studied dwarf galaxy had to move away from the void and towards large concentrations of matter. Some experts suggest that the local void is expanding steadily. Consequently, this constant displacement also has an effect on our local Milky Way. It moves away from the local void at a speed of 168 miles per second. Dipole repeller. However, the large local void is not the only exciting space area we would like to introduce to you today. The so-called dipole repeller has also been making the scientific headlines ever since its discovery in 2017. At that time, an international team of researchers succeeded in identifying a structure that exerts a dominant influence on the local group. For in fact, this sparsely populated region of the universe occupies a repulsive role. All galaxies located around this region drift away from it. Thus, the velocity difference of the local group with respect to the background radiation is reported to be over 390 miles per second. The Shapley supercluster also produces an effective force on the motion of the Milky Way and its surrounding galaxies. As the largest known collection of star systems in a radius of 700 million light-years, this center of mass ensures that the associated star systems are gravitationally held together. At the same time, the discoverers of the dipole repeller succeeded in detecting another cosmic void that also has a repulsive effect on the surrounding structures, the cold spot repeller. Such gigantic voids, which apparently repel matter, are among the main components of the cosmic velocity network. The riddle of the voids. As already briefly mentioned, the areas surrounded by the filament net are called voids. But how is it actually possible to explore these galaxy-poor regions within the cosmic honeycomb structure? Every scientific work which deals with the origin of these formations on the larger scales must consequently also explain the origin and distribution of the voids. These areas bring it on extensions of 326 million light-years. If the velocity of a galaxy were calculated at 375 miles per second, the accumulation of stars, planets, and company would need more than 160 billion years to pass such a void completely. For classification, the universe itself is only 13.8 billion years old. In view of this, it appears as exceedingly improbable that the formation of the voids was in connection with the directed proper motion of galaxies. Rather, it appears that the voids reflect the distribution of galaxies at the time of their formation. The problem here, however, is that the baryonic matter interacting with the radiation was far too homogeneous in the early cosmos to gravitationally form such structures. Because of this, some researchers argue that it was dark matter that had a significant influence on the structure formation of the voids and filaments. Unfortunately, this ominous form of matter is still an unsolved mystery. In the standard model of cosmology, dark matter is consulted to explain the motion of visible matter. This is especially true for the speed at which stars orbit the center of their galaxy. Although dark matter plays a fundamental role in the cosmos, it only reveals itself through its gravitational effect on gravity motions. It remains invisible and has not yet been directly detected. In order to understand how the dimensions of a filament are reflected in reality, it's worth taking a look at the constellation to which we also belong with the Milky Way. Thus, the members of the local groups, together with other galaxy groups in the vicinity, and the centers of the Virgo cluster, the Coma cluster, and the Leo cluster, form a gigantic filament. This net-like structure, in turn, moves toward the aforementioned Shapley supercluster and the so-called Great Attractor. Unlike structures such as the dipole repeller, this supercluster, which is one of the most massive structures known, has an attractive effect. This means that the galaxy clusters within this collection drift apart less rapidly than would be expected if the cosmos were homogeneously expanding. Although the Great Attractor has an intrinsic mass of 10 quadrillion solar masses, this alone is not enough to explain this mysterious effect. Therefore, scientists suspect that other sources of attraction exist in the region but are obscured by the Milky Way. repulsion and attraction. In a universe that has a homogeneous mass distribution, the gravitational forces acting on a location should cancel each other out. Thus, within such a scenario, there could be no acceleration component. However, the actual matter distribution of the cosmos draws a completely different picture. Thus, there are areas in the universe whose mass concentrations appear to be above or below average, galaxy clusters and voids. Consequently, it's in the nature of the thing that galaxy clusters possess an attracting effect in the direction of matter. In turn, the lack of mass within voids is accompanied by a lack of attraction. The result of this constellation is a force acting in the opposite direction. If we want to investigate the velocity of our local group, we must not only consider the attraction of the Shapley supercluster and the Great Attractor, but also consider the apparent repulsive effect, which a void has on the cosmic accumulations in its proximity. Recent calculations even suggest that the repulsion has a larger influence than the attraction forces of the galaxy clusters. Accordingly, the corresponding motion vector points precisely away from the void, while at the same time pointing only in the approximate direction of the large mass concentrations. It is July 5th, 2016, and NASA's Juno spacecraft is entering orbit around mighty Jupiter. Since that day, the 3.6-ton, $700 million instrument has been taking a close look at the largest member of our planetary system. Equipped with complex measuring instruments, Juno gives us an unprecedented insight into the most massive planetary world in the solar system. But what discoveries has the probe already made in the realms of the gigantic gas giant? And why did a certain circumstance astonish terrestrial scientists? Together with you, we are looking for answers today. The king of the solar system. Mighty Jupiter has an equatorial diameter of 89,000 miles. For comparison, in theory, our blue home planet would fit into the gigantic celestial body more than 1,300 times. Just like Saturn, Uranus, and Neptune, Jupiter does not have a solid surface. Due to its volatile chemical composition, it's classified as a gas planet. If we take a look at the giant celestial body, we immediately encounter a striking optical feature: numerous band-like formations which present themselves in the most diverse hues. In detail, these fascinating structures are clouds located in the tropopause of the gas giant and containing ammonia ice crystals. It's thought that it's these frozen ammonia particles that give the lighter bands, the so-called zones, their characteristic coloration. Why the other areas, which are called belts, show themselves so much darker has not yet been clarified. Current suppositions say that this is due to chemical components, among them sulfur, phosphorus, and possibly hydrocarbons. In fact, these fascinating cloud bands are by no means rigid structures. They move steadily in an easterly and westerly direction. The thunderous boundaries of these structures are the so-called jets, strip-shaped areas with high wind speeds where whipping hurricanes develop again and again. The upper layers of the planetary king of the solar system are mainly composed of hydrogen and helium. In much smaller quantities, there is also ammonia and methane here. In addition, however, traces of many other elements have been detected, such as sulfur, carbon, and oxygen. At an average distance of 483 million miles from the Sun, Jupiter needs 11 years and 365 days to completely orbit our host star. Although this massive celestial body is nearly 2.5 times heavier than all other members of our planetary system combined, it has the fastest rotation. It takes just 10 hours for the gas giant to rotate around its own axis. Due to their volatile chemical nature, the rotation behavior of gas planets cannot be compared to that of solid celestial bodies. While the regions at the equator need about 9 hours and 50 minutes for a rotation, the polar regions estimate about 5 minutes more for this endeavor. A look at the research history shows us how important the direct investigation of Jupiter is. Until 1980, only 16 satellites of the planet were known. Thanks to the Voyager probes and the current Juno mission, however, we know that Jupiter is accompanied by at least 79 moons. So let's now take a closer look at some exciting discoveries that have already been recorded on the gas giant. The decoding of the gas giant. Over time, Jupiter has been approached several times by unmanned spacecraft and explored in depth. From the Pioneer space probes to the Galileo mission, to the current Juno mission, each of these complex pieces of equipment helped us get a little closer to deciphering the gas giant. And yet, despite all the research missions completed, the mighty celestial body still hides many secrets. These include some exciting weather phenomena that are as impressive as they are puzzling. Let's take a look at the famous Great Red Spot. This gigantic high-pressure area is 1.5 times the diameter of our blue home planet. A look at the observation history of the Great Red Spot shows that it's by no means a fleeting phenomenon. According to this, the structure was possibly already described in the year 1664 by the English polymath Robert Hooke. For classification, earthly wind vortices in the atmosphere usually disappear within a few weeks. Why the oversized structure presents itself in a rich red color is unknown. What is certain, however, is that the Great Red Spot is changing. Observations by the Hubble Space Telescope showed that the anticyclone had a reach of 10,300 miles in spring 2014. By comparison, the structure had made it to 25,000 miles in this category in the late 19th century. Already suspected in the run-up to the Pioneer 11 mission, an exciting assumption was confirmed by the Voyager 1 mission. Jupiter has its own ring system. However, this system is much more sparse than the complex thousands of bodies orbiting Saturn. The origin of Jupiter's rings was an unsolved mystery for a long time. Only the Galileo probe succeeded in shedding some light on this cosmic darkness. According to this, the dusty base material of the rings most likely originates from the small rocky satellites that accompany Jupiter. In fact, the satellites are subject to a constant bombardment of meteorites. The material that is stirred up as a result of the impacts subsequently enters the orbit of the gas giant, where it replenishes the existing orbits with steady supplies. Secrets inside. As is so often the case with Jupiter, the greatest secrets are initially invisible to the research eye. By this, we mean those structures and formations that are hidden in the innermost regions of the gas giant and consequently cannot be deciphered at first glance. Before Juno left our terrestrial home on August 5, 2011, it was given a number of overarching research goals. Among other things, the spacecraft was to find out the details of the atmospheric distribution of chemical elements. Convection, or in other words, the flow transport of gases, was also to be examined in detail. In addition, the question of the origin of Jupiter's magnetic field had to be answered and the polar magnetosphere analyzed. However, one of the most exciting questions discussed in the run-up to the Juno mission was that of the solid core. Scientists' models suggest that the gas giant has a massive heart, composed of rock and ice, with up to 20 Earth masses. The researchers were all the more amazed when they received the first measurement results from Juno in this regard. In fact, the real data differed significantly from the theoretical considerations of the experts. There was simply no trace of a solid rock core, which clearly exceeds the mass of our Earth. In fact, the scientists discovered nothing that looked like a core. This caused quite the confusion in the ranks of researchers. It did not last long, however, before an initial explanation was proposed for this mysterious circumstance. Possibly, the gas giant possesses a core, but perhaps this is not at all concentrated in the center of the celestial body. Possibly the planetary heart of the gas giant is much larger than the researchers had assumed in the scope of the mission. Some theories say that the planetary core is perhaps even half as large as Jupiter itself. Enigmatic auroras. They are among the most enchanting spectacles our terrestrial home has to offer. Auroras. Since 1979, we have known that these are by no means a phenomenon exclusive to Earth. The so-called auroras also occur on Jupiter. We know from our home planet that the dancing luminous phenomena are caused by high-energy charged particles interacting with the Earth's magnetic field. However, how the Jupiter polar lights are formed is uncertain. Since the auroras of the massive gas giants are incomparably energetic, they mainly show up in the UV and X-ray range. While Juno analyzed the celestial body's magnetic field, a team from the Chinese Academy of Sciences observed the phenomenon using the XXM Newton Space Telescope. As part of their work, the experts discovered evidence of so-called emic waves. These are instabilities in plasmas. The collected data suggests that the electromagnetic waves in Jupiter's magnetosphere have a direct influence on these emic waves. Furthermore, the experts suspect that, in addition to the solar winds, Jupiter's moon Io also plays a fundamental role in the formation of the aurora. According to this, the satellite acts as a kind of natural particle supplier. The satellite is volcanically active, and the sulfur dioxide gas emitted in the process gradually enriches Jupiter's magnetosphere with oxygen and sulfur atoms. Now, the emic waves could in turn cause the corresponding atoms to be scattered, race along the magnetic field lines to the polar regions, and finally create fascinating luminous phenomena in the X-ray spectrum there. Should this assumption be confirmed in the future, the Earth and Jupiter would be amazingly similar, at least in the area of auroral formation. Exciting findings. Given the great mysteries that still surround Jupiter, one might think that the research missions so far have provided more new questions than answers. However, we should not forget at this point that Juno's mission, of course, also helped gather important knowledge about the largest member of our planetary system. When Galileo studied Jupiter's atmosphere in 1995, it appeared unexpectedly dry. In fact, 10 times less water was detected there than scientists had previously assumed. Thanks to Juno, we know that water is abundant near Jupiter's equator. The mystery of lightning has also been unraveled during the current mission. Past space probes exclusively detected lightning on Jupiter at unexpectedly low radio frequencies. Since the Juno spacecraft studied the planet from a greater proximity, it finally succeeded in detecting lightning with higher frequencies as well, thus solving a mystery that is about 40 years old. In addition, we now know that Jupiter's North Pole is graced by a structure that is both appalling and exciting, a gigantic cyclone framed by 8 others. Now it's time for your opinion. What do you think about the fascinating gas giant Jupiter? Drop us your thoughts, your suggestions, and your feedback on today's video in the comments below. Finally, feel free to take a look at the other posts on our channel that we've linked here for you. Thanks for your interest, take care, and we'll see you next time.